Hello, my name is Shaked Brody and this is joint work with Uri Alon and Eran Yahav. This talk is about a novel structural model for contextual code changes. In this work we present the edit completion task. Imagine that you are working with your favorite IDE and you are about to change the following method in such a way that it will return a file characteristics object with a return statement rather than with an output parameter. In the first step, we are replacing the return type bool with the file characteristics type. In the second step, we are removing the output parameter. In edit completion, we want to predict what is the next likely edit. Since the file characteristics was removed from the parameter list and the return type of the method was changed to file characteristics, it is likely that the return statement should be changed as well and contains a file characteristics object as a return value. This part is what we are trying to predict with edit completions. In this example, our approach predicted the completion that you see here. So in edit completion, given a contextual code edit, delta C, we want to predict the next likely edit, delta P. To perform such predictions, we train a neural model with tens of thousands of pairs of contextual code edits and edits that appear next. This is done in hope that at test time, the model will be able to generalize well to unseen examples, such that when it sees a new example of contextual code edit, delta C prime, it will manage to predict the next likely edit, delta P prime. To address this problem, we have to tackle two main challenges. The first is how to represent code, and the second is how to represent code edits. As we will see soon, these decisions affect dramatically on the performance of such a model. There are two common approaches for representing code. In textual representation, we treat the code as a flat token stream, the same as humans read code. In structural representation, we represent the code by using its underlying abstract syntax tree, or AST in short. Previous work showed that using the rich structure of the AST can benefit trained models in code-related tasks such as code completion and predicting method names. In tasks that require predicting code edits, such as edit completion, the output can be one of the two forms. In code likelihood, given the code before the edit, X, we model the likelihood of the whole code after the edit, Y. The output of such a model is the complete code after the edit. As opposed, in edit likelihood, we model the likelihood of the edit itself rather than the code after the edit. Given the code before the edit, X, we model the likelihood of the transformation function delta, which transforms X to the code after the edit, Y. By using edit likelihood, we make the task much easier. While in code likelihood, the trained model must learn to generate the entire code after the edit, in edit likelihood, the model only needs to learn what the edit operations are. Since these operations are defining a deterministic transformation, we can apply them to get the code after the edit. This table summarizes the two dimensions we talked about in the last two slides. By combining code representation and edit representation, we get four different approaches for solving tasks like edit completion. In textual representation and code likelihood, the input is in the form of text, and the output is the whole code after the edit in textual representation as well. In textual representation and edit likelihood, the input is text, and the output is a list of textual edit operations that can be used to transform the code before the edit to the code after the edit. In structural representation and code likelihood, the input is the AST of the code before the edit, and the output is the whole AST of the code after the edit. Finally, in structural representation of code and edit likelihood, the input is the AST of the code before the edit, and the output is a series of structural edit operations that can be applied directly to the AST of the code before the edit in order to get the AST of the code after the edit. In this work, we show that choosing the last approach performs best compared to the other approaches. So how do we represent structural edit operations? Consider the following edit, where was updated to first, and the last call in the call chain was deleted. We can represent this edit using structural edit operations over the AST of the code before the edit. The first operation consists of updating the value of the node where to first. Since a node with a value first is present in the AST, we can use a path between the two nodes to represent this update operation. Next, we delete the dot node. To do this, we are moving this node to the trash node del. By drawing a path between the dot node and the del node, we can represent this operation. Similarly, we can represent the removal of the call node alongside its subtree with a path between call and the del node. This example shows how we can represent structural edit operations by using AST Paths. Representing edit as paths allows a learning model to generalize well across different examples. In this example, we can see how two different edits are represented almost identical when using the structural representation of code and edit likelihood modeling. In the right figure, the path that represents the update of where to first or default is almost identical to the path that represents the update of where to first in the left figure. In addition, the other two operations representation is identical in both examples. This property helps a trained model to generalize better on unseen examples. We implemented our approach for edit completion in a neural model called C3PO, short for Contextual Code Changes via path operations. The input for the model is a sequence of AST paths that represent the contextual changes. The model uses a pointer network to point to AST paths in P, which represent valid edit operations. The model also attending to the paths that represent changes in the context while pointing to paths in P. Our model is lightweight and contains only 750,000 learnable parameters, which result in a fast training phase of only 9 hours of training. To train our neural model, we scraped the whole commit history of the most popular C# repositories from GitHub. From each commit, we extracted edits from C# files alongside their contextual edits. This results in 40,000 examples of train, 4,500 validation examples, and 6,000 samples test splits. Our code dataset and trained models are publicly available at GitHub. We evaluated our model with strong baselines, which can be classified by the two properties of code and edit representation we discussed earlier. We implemented each baseline twice, where one version is based on LSTM and the other version is based on transformers. So here we can see the results of our evaluation. Greens are textual representation and code likelihood, reds are textual representation and edit likelihood, blues are structural representation and code likelihood, and purple is structural representation and edit likelihood. As we can see, our model gains more than 11% absolute accuracy over the strongest baseline, which is laser tagger with transformers backbone. These results emphasize the need for structural representation of both code and edit. In this example, we can see how the edit in the method signature affects the needed edit in the body of the method. The context includes the following edits. The modifier public was changed to private. The return type was updated from file characteristic to base file appender, and the method name was changed to get appender. On the right, we can see part of the method's body. Since the return type of the method was changed, the return statement in P must be changed as well. The renaming of the method to get appender may have also hinted to our model that an appender object should be returned. Our model successfully predicted a desirable edit, which is changing the return statement to return an appender object. This example shows how context edits are important in predicting edits in a program by providing information about the changes in the return type and the method name. Here we can see how the edit in the context is conceptually similar to the edit of P. On the left, we can see a variable declaration statement where part is cast to the type method call expression and assigned to a newly declared variable method expression. In the edited context, the keyword var was updated to the explicit type method call expression. On the right figure, we can observe a similar edit of an initialization statement where the variable name parts is assigned a new stack of strings. Using the change in the context, our model predicted the edit of var to the explicit type stack of strings. The edit consists of insertion of a new subtree since stack of strings is represented as a subtree of 5 nodes. In contrast, the edit in the context is represented as an update edit because it only needs to update the value of a single node. This example demonstrates a class of examples where the edit in the context hints edits that are similar in spirit in P, but are not identical and should be performed differently. In this work, we present a novel approach for representing and predicting edits in code. Our focus is on learning the likelihood of the edit itself, rather than learning the likelihood of the new program, while using a structural representation of the code. We show the effectiveness of our approach by using the edit completion task. We present a novel neural model for addressing the edit completion task and show its superior performance compared to other strong baselines. We use AST Paths to represent code edits that occur in the given context and use these paths to point to edits that should be predicted. We believe that our approach can serve as a basis for a variety of tools that require the modeling and prediction of code edits. We made our code dataset and trained models publicly available at GitHub. Thank you for listening.